Hello everybody, this is going to be the video for Intro to Area Under a Curve. This is going to be for pages 11 through 14 in your packet. You may need a calculator, but most likely you won't. And we're going to go in and get going. Oh, also, I'm sorry if I make gross sounds during the video. Still a little bit under the weather. And my wife is also coughing in her room, so this is going to be a gross video, in other words, but at least you won't get infected. Okay. What were two major questions the mathematicians were looking to solve with calculus? This is on page 11. Two questions that they were obsessed with about calculus is one, the instantaneous function at a particular that they were obsessed with. Okay. Second one was finding the area between a curve and an x-axis. Now this is what we're going to do today. So we have these pictures here because I just sometimes area between the curve and the x-axis is easy to find. So for instance, for this line, you're bounding the area between the curve and the x-axis. You're going to hear that word a lot. We're just looking at the area of this right. We're looking at the area of a line between the curve and the x-axis. We're just looking at the area of a triangle. So these aren't really that difficult. This is not the ones that, or two triangles really. This is not one that mathematicians had a hard time with. However, for an arbitrary function like this, though, arbitrary meaning random, for an arbitrary function like this, that's a tough one to find the area of because, I mean, I can't really use circles, I can't really use triangles, or I'm just thinking of different ways that I found area before. And in fact, what they've come up with is you could actually find the area of any function using rectangles. And there's a whole key to it that you'll see afterwards. It's really, really cool. And I'm not being sarcastic. It is a really, really cool concept. Okay, now this was the last one of, again, just trying to find area between a curve and some other shape. Okay. But this picture is fun, but it's not relevant for us. So mathematicians used rectangles and trapezoids to find areas of regions that were unknown of how to find the area. And we'll see what that means. Our goal for this video is to find the area of the region under the curve that is defined under the curve between the curve and the x-axis. So between curve and x-axis. That is defined by the function f of x equals negative x squared plus 5, and that graph's given to you. That is also bounded by x equals 0, x equals 2, and y equals 0. Before we go on, I want to go over that because this will come up later on. X equals 0 is this line. X equals 2 is the green line. Y equals 0. Let's go and draw these all the way down here. Y equals 0 is going to be this red line. And the curve. The curve will be purple. When it says bounded, it's only looking for the region that is contained by all the colors that I just did. So I'm looking for the area of this region. And we'll practice that bounded part later on when we get closer and closer to the AP test. Okay, so let's go ahead and see how we can find the area between a curve and an x-axis. Again, reminder that our function is negative x squared plus 5. Let's estimate with one rectangle. So a left-hand rectangle looks like this. Remember, I'm looking at the interval from 0 to 2. Okay, that's where I'm cut off by. One left-hand rectangle is going to look like this. I start on the left side of the function. And if I want one rectangle, I draw all the way to the side here and down. Because I want the rectangle to cover one whole, just the entire area. So this area would be a length of 2 on the bottom. Okay, so 2. And I'll go over with the right-hand rectangle why it can't be any different. So 2 times, I'm going to do f of 0. The reason I'm doing f of 0 is because this point is the height of the rectangle. Gives us the height of the rectangle. That's f of 0. F of 0 is 5. So 2 times 5, that's 10. So that's the area of the left-hand rectangle. For a right-hand rectangle. So now let me go over why it can't be anything else. Why I can't draw the rectangle in any other way. And I want to talk about left-hand, right-hand too. So for the right-hand rectangle, I start on the right side of the function at the end point. I can't start over here because I miss an entire portion of the curve. So I can't start over here. I have to start where the function ends. So right means where the function ends. And I just draw a nice horizontal line from there, and I have to cover the entire interval. I have to cover that interval from 0 to 2. I can't shortchange it. So from 0 to 2, it looks like I have 2. Again, that width is 2, and the height is going to be f of 1 this time. That's false. It has to be f of 2. The reason it has to be f of 2 is because the x value is 2 here. So let's do 2 times f of 2. And keep in mind, f of 2, f of x is negative x squared plus 5. So let's do negative 2 squared plus 5, which is going to be equal to 1. So 2 times 1 equals 2. Now, neither of these rectangles is going to give me the exact area between the curve and the x-axis. One over approximates by a long shot, one under approximates by a long shot. So let's see what happens if we have two rectangles. So first of all, again, the way we draw our rectangles, we want equal width. We're still in the interval from 0 to 2. So what I need to do is I need to take 2 minus 0. I need to take these endpoints of 2 and 0, and the reason they're endpoints again was the bounds. I need to take those endpoints and divide them up evenly. So this was this numerator is the interval, and the denominator is the number of rectangles. Okay, so if I do that, I get a length of 1. So that means I'm going to draw 1 at 1 because this is a length of 1, and from 1 to 2 is a length of 1. And I'm covering the entire interval. Now to do a left-hand rectangle, I'm going to start again at the left corner. So notice again, the left-hand rectangles are at the left corner. That's worth jotting down. Left corner is where you want to start. Okay, so left corner, and then draw out and stop at that first interval. And now the second point is going to be, the second rectangle is going to start right here because the point always has to be on the curve. So draw that second one horizontally. And those are your two left-hand rectangles. And again, we classify left-hand rectangles by seeing that the left corner of the rectangle is on the function. Okay, so let's get our area here. Our area would be 1, because our width is 1 now, times f of 0 plus 1 times f of 1, which is going to be 1 times f of 0, which is 5, plus f of 1, which is 4. So now we get 9. Not much better than our estimate of 10 from the last time, but decent. So now let's go and do the other one. I'll go and erase this, but you'll have to draw it in on the same graph for yours. The intervals don't change, but I need to make sure that I'm doing right-hand rectangles here. Okay, So I need the right corner of the rectangle to be on the function, and I draw a little box. Again, a right corner right there. And then I go up, and there's my right corner again on the box, and I draw a rectangle to the left. Okay, so hopefully you were able to get your pictures for this. This is the area that I'm looking for. Still doesn't capture exactly the area that I'm looking for, but does a decent job. So I take, the width was still 1, times, this time, my height is at f of 1 and f of 2. So let's add those up. Okay, f of 1 was 4. F of 2 is 1. And I get 5. So I went from 10 to 2 to 9 to 5. So now a question could be, well, if I add more and more rectangles, what's going to happen to these numbers? And it looks like they're getting closer and closer, somewhere in between 10 and 2 and 9 and 5, more particularly between 9 and 5. So what we're going to do on the next page is add even more rectangles. So let's do it. Okay, we're going to use this top picture for 4 left-hand rectangles and this bottom picture for 4 right-hand rectangles. What I'm going to have you do is pause the video, talk it over with your groups, and see if you can get an answer for this. One thing that I want to make sure you're using is when I set up my areas, I always did f of 0 and f of 1. I did not write down f of 5 and 4 first. I always want to put it in terms of the function for the height. So please make sure you're doing that. Please make sure your group members are doing that. And then the other thing I want to bring up is this 1 was on the outside because the width is uniform for both of them. The width is always 1 for both rectangles. So I can take a 1 out of both heights, and it's just a little bit easier. Okay, please pause the video and try 4 left-hand rectangles and 4 right-hand rectangles. And talk it over with your group. Okay, hopefully you were able to get your answers and check with your groups, etc. Here's what I got. So again, the interval's from 0 to 2, which means my width has to be a half for each one. Okay, that's what the rectangles look like on the graph. Here's my setup. And again, I must see this part. I want to see that part. If I don't see that part, that's going to be a problem for you. If I see that part, I'm going to be very, very happy. F of 0 plus f of 1 half plus f of 1 because I want the height in terms of the function. Okay, and then that should be my answer. If I got it wrong, you'll let me know next time. All right, next. Here's the 4 right-hand rectangles. And again, same process. It looks like the graph will look like this. And the answer should be 6.25. I'm not going to explain why for each one. Please talk it over with your group members for why. And those are our table values. Now, what our goal is, remember, is to make sure that we can get the exact height, the exact area between the curve and the x-axis. So how do we do that? Well, it's going to be magical. And I'm going to stop this and make sure and have you watch a second video.